Let's turn our attention to analog I/O modules within the PLC. The concept of analog in a PLC is something that you really have to spend some time on because there are multiple facets, multiple sides to it. In the first place, the PLC is basically a computer that only has on-off things, right? It only has switches. So how do you represent something that is an analog signal, where analog has multiple different levels? How do you represent that when all you really have are on-off types of things? Well, if you know anything about binary, you know that this problem is already solved. You know that computers use switches essentially internally, and it uses groups of switches to represent numbers. So you can represent numbers with on-off signals pretty easily. I'll use a crude explanation here, pardon me, but you see my hand and you might wonder, well, how many can I count up to on one hand? And you might say, well, 5, of course, 1, 2, 3, 4, 5. Well, actually you can count a lot higher than that, because you can use base 2 math, where you can count up to the base 2 to the power of the number of digits you have, in this case 5. And that's how many numbers you can represent. So 2 to the 5th power, if you do the math, that's 32. The numbers you can represent are 0 through 31. Those are 32 separate numbers because 0 is itself a valid number. So pardon me, I'll have to make some crude gestures here along the way. But to illustrate, you can see that this would be 0. There's 1, 2, 3, pardon me, 4, 5, 6, 7, 8. Some are harder than others, but you can see once all 5 bits, binary digits, are on, well, then that would be the number 31. So 0 to 31. And if you have 5 more bits, well, it turns out you take 2 to the power of the number of bits, well, that's 10. And the number, well, I'll let you do that on your calculator and see how many different numbers you can count up to with 10 fingers. So there has to be something to take the analog signal and convert it to digital, and what's used there is called an analog to digital converter, an ADC. And so that's basically the main thing that is inside of the analog input module, is an analog to digital converter. And so what it does is measures analog signals that are continuous in nature. Now, things like the level in a tank, the pressure, the temperature, all these different very common variables can either be looked at as discrete, where say the temperature is above or below a certain threshold, or continuous things where, no, we're not looking at a threshold, we just want to know what the temperature is, and that can take on a range of values. In a furnace, for example, maybe the temperature is anywhere from 0 to 2,000 degrees Fahrenheit. So analog signals themselves have an infinite number of values, but they're sampled inside of the analog input module, so that there's only so many different levels, and often you have to decide how many levels you need, and that's where a resolution question must be answered. But how does the signal get from the sensor itself to through the level transmitter or a transmitter into the analog module? Well, typically what's used is either a voltage or a current signal. So these are often done electrically, though in the past electrical signals were not the only types of signals. There were pneumatic signals, air-based signals, signals that were pressures, but they weren't, say, a pressure in a tank that you were trying to measure in a process. They were just a pressure signal, say 3 to 15 psi, that indicated a measurement of a certain amount. Now, pressure signals are not all that common anymore for transmitting information throughout a plant. What is much more common today is electrical signals, and they, as I said, come in two flavors, current or voltage signals. And we'll see a little later why current signals are preferred, but there are typical ranges of these that are common. Either 0 to 20 or more commonly 4 to 20 milliamp signals are often used for taking information from a sensor to an analog input module, or even a voltage signal of 0 to 10 volts, or even perhaps 0 to 5 volts. You might know that 0 to 24 volts is commonly used with PLCs for discrete control, but 0 to 10 volts is more common for analog control, where the signal varies continuously. It's not just a 0 or 10 volt signal like a discrete 0 to 24 volt signal. No, it's 0 all the way through any voltage level in between 0 and 10 volts to represent the analog signal itself. So what the analog input module does is basically sample, it measures the voltage or the current and converts that into a number, a digital number. So there's some information that's lost because the sensor or the module may not be able to tell the difference between, say, 5.8239 volts and 5.824 volts. Okay, it may not have that high of resolution. So there's some round off that occurs, but that's a question that you as an engineer have to answer. How much round off is acceptable? In other words, what's the resolution that I need for measuring the magnitude of this signal? How much pressure variation do I need, for example, or temperature variation do I need to be able to detect? And most of the time, analog to digital converters work with a high enough resolution that it's not really an issue. Most of the time the modules have much higher resolution than most processors need. But there's another kind of resolution to think about besides the analog resolution, and that is that these analog input modules are not just constantly taking in continuous streams of data. What they're doing instead is waiting a certain amount of time and then measuring the voltage or current, and then waiting and measuring again, and so forth. And so not only is the analog signal discretized in amplitude, it's discretized in time. And so you have to know what measurement frequency is necessary for the process to run well. Now, analog output modules act on the other end of the processing in the PLC, and what they do is take a number within the PLC and convert it to a continuous output signal. Obviously, this is a discretized signal as well in time and amplitude. And so maybe your analog output module drives a level indicator, or maybe it drives a valve, a proportional valve. And so the valve's not on or off, it's some percentage of on or off, and that can be driven by the PLC. Well, the job of the analog output module is to take the discrete numerical value that represents the valve's position and maintain it as an output to the valve continuously. So it converts a digital signal into an analog signal. So the two basic sensing modes are voltage and current sensing, but often sensors, the detail of sensors themselves, require that you have special either circuitry between the input module on the PLC and the sensor, or perhaps a special type of input module. And one common type of input module that's special is a thermocouple input modules. Thermocouples are temperature sensing devices. They really just consist of two dissimilar metals that are touching, and when that junction is exposed to varieties of temperatures, different levels of voltage signals are generated by the sensor. It's very small, we're talking millivolts. And so the typical analog input module on a PLC cannot detect a millivolt signal, something that small, and so it has to be amplified, and that is either done by a transmitter or it's done internally in a special analog input module that accepts thermocouple inputs. Now, of course, that's an example of a voltage signal, but there are also current signals. Now, in an analog input module, another thing to consider is whether it accepts a signal that is bipolar, unipolar, and what the resolution is. Now, bipolar, what that means is that the level of the signal can go positive and negative. So maybe current can flow forward and it can be made to flow backward. That's not common. It's not very common to have a bipolar current signal. What's a little more common is a bipolar voltage signal, where the voltage can go above a reference and below that same reference. Now, this is much more common in audio, and I'll show you some examples of that later, but bipolar signals are signals that can go above and below a reference level. Unipolar is by far more common in industry, where the input module only accepts signals that go up from zero, so zero and up to a certain maximum range. So 0 to 10 volts would be common, negative 10 to positive 10 volts would not be common, but they are available in, say, a negative 5 to positive 5 volt. That would still be a bipolar voltage signal, but what would be much more common is a 0 to 10 volt or a 0 to 5 volt unipolar voltage signal. Now, another really important thing to consider, as I said, is resolution. In other words, what's the smallest change in the actual input signal, the voltage, that can be represented within the PLC, where the number changes from, say, 2000 to 2001 inside the PLC. And that resolution is something that's really important to consider when you're selecting a analog to digital conversion module, so that you can sense fine enough detail within the process to effectively control the process. Now, current signals are much preferred to voltage signals, and the reason why becomes apparent when you consider that sensing devices have to be mounted on the plant. So the plant might be, let's talk about a plant that's large, something where they're making rubber, like down at American Synthetic Rubber Company. I only use them as an example because I've toured their facilities. They're located over in Louisville, Kentucky on the west end, or toward that end. Well, it's a big plant. I walked around it. It was fairly cold. We went there once with the SME group, and it's a large enough plant that it took us about an hour or two to get around the whole thing and see the entire process. Well, the process requires measurements of temperature and pressure and all sorts of chemical composition things, and so there are sensors mounted on this plant. Just, we probably walked a couple of miles that day, and all of this is far away from the control room where the PLCs and the controllers are located. So how do you get this sensor data from the sensors themselves back to the controller so the controller can do what it needs to do in terms of making decisions about how far to open valves and setting alarms and things when everything's apparently out of control or something's out of control? Well, you have to use some type of electrical signal. The problem with voltage signals, if you have, say, a 0 to 10 volt signal coming out of your sensor, it has to be connected back to the PLC by wire, and copper wire is most common. But even copper wire, though it's a good conductor, has resistance, and so what will happen is that voltage signal will actually decrease. Say your sensor's out a mile away from your PLC. If you've got a mile of copper wire and only a 10 volt signal, I guarantee you that signal, the voltage is going to drop by the time it gets back to the PLC. So what is, represents full open or full on, maybe an 8 volt signal or so, or very highly on, might become a 4 volt signal by the time you get back to the analog input module, and so the voltage signal degrades over the wire because of the resistance of the wire, and so it doesn't look like the valve is fully on or the whatever temperature we're sensing. It looks like it's just partially on, and that's not acceptable. We need to have accurate measurements of the process. So if you use a current signal, what happens is the sensor either has a power supply or it's the module itself provides power, but in any case, what the sensor does is it supplies a 4 to 20 milliamp signal back to the PLC, and what it will do is it actually has internal circuitry that detects how much current is flowing. If not enough current is flowing through it, it will actually increase the voltage across its terminals to force more current to flow. And so despite the resistance in the wire connecting the sensor to the PLC, what will happen is the sensor will increase the voltage across its wires so that it guarantees that the right amount of current, indicating the measurement of the sensor, whether it's temperature, pressure, whatever, is sent properly back to the PLC. So you can see two different scenarios here, one where the power supply is connected directly to the sensor, and one where the power supply is more connected to the PLC itself. They work in a similar fashion, and in any case, the sensor senses the current flowing through and makes sure that its own resistance, in the case on the right hand side, is low enough that current actually flows through and represents the signal accurately, whatever the sensing happens to be, whether temperature, pressure, or a valve's position, or whatever it is. Now, in order to reject noise, because current can actually be induced on the wire from other wires running parallel to it, so what's commonly done is shielding is added, and that shielding is grounded on one end to electrically insulate the wires from any other sources of current that might induce current onto the wire. They're also typically twisted, and what that does is that causes any noise to affect both wires equally and ends up canceling out. So this is common practice, but 4 to 20 milliamp signals are the most common, just because they don't degrade over distance. Another thing to note about this is, you notice it's 4 to 20, not 0 to 20. Why would we have why would we represent, say, no pressure as 4 milliamps instead of 0? It would make more sense to have it as 0, right? Actually, not really. Think about it. If the sensor fails, then the amount of current going through the wire will be 0, and that would be a fault condition that could be recognized by the controller, by the PLC. If there's no current at all flowing through the loop, that doesn't mean that the pressure is 0. That means the sensor's broke. and that's worth knowing. So 4 to 20 signals, 4 to 20 milliamp signals are by far the most common, although there are other signals nowadays where sensors can be set up where they're more on a network and they actually transmit information to the PLC about their measurements and their functioning and so forth, and this is becoming more and more common. But if you ever work in a plant, you'll see 4 to 20 milliamp signals many places. They're still very common. On the output side of things, we have to have some digital to analog converter. And what this thing has to do is receive digital data from the processor. Say you want the valve to be a certain amount of open. Well, it has to send a signal proportional to the amount that's needed in either voltage or current to an amplifier on the valve that actually positions the valve in accordance with the set amount that the analog to digital converter is demanding, which of course comes from your program. And so there's all kinds of analog output devices that can be controlled, but basically, as I said, the purpose of this digital to analog device is to maintain a continuous voltage or current signal out to the final control element that is proportional to the demand from the PLC. Now here's an example of an analog I/O system where there's a level sensor going into the PLC and a valve that controls flow into a tank. Now of course it's not shown here, but we're assuming there's flow coming out of the tank continuously, and who knows what the purpose of this process is. But the PID controller would exist inside of the PLC. Many PLCs have commands built into them to make PID control within the PLC very easy and simple to program. So let's imagine that the valve is initially open 100%. As the level goes up, and this level sensor wouldn't just be an on-off thing, it would sense continuous values of the level. What the PLC could do is sense, oh well, the tank is filling up, and so I'm going to clamp down on that valve. The valve's not an on-off thing, but the valve would start to be closed off to resist the flow in, or decrease the flow into the tank if the level gets too high, or increase the flow into the tank if the level gets too low. And of course this all involves PID control, but there's a continuous variable being measured, which is the level in the tank, and a continuous control element, the valve. Neither one of these things are completely on or off. They can be varied between 0 and 100%.